In this session, our last speaker is Keyan, and he is working in London, although he's American as far as I understood. And he's here second time on this show, this time as a speaker, and we say thank you very much for this. And he will bring us in the world of big facades, right? We will hear about the world largest bent facade in the world. You can see it already. And Keyan, the floor is yours.
Thank you. All right, so yes, my name is Keyan. I am with Front Inc., which, if you're not familiar with Front, Front is a global facade consulting agency, and we have projects all around the world. We're based in London, Hong Kong, New York City, and we do all manner of, whether it's high-rises, special structures, we consult on all kinds of projects doing technical analysis, structural analysis, system design, thermal analysis, any manner of kind of facade consulting and technical analysis and consulting. You can see we work on all kinds of projects now. I'm going to come back to these a little bit later, but these are a class of projects we have in our portfolio where we were working on delivering the project in tandem with the contractor, which is something that will come up later. This is kind of like the second generation of those projects, but just to give you a sense of kind of what led us up to this point, which is the Lusail Plaza Towers, which are in Doha. It's a set of 4 high-rise towers, which are feature cold bent glass, very complex geometry. Every single panel is unique. I will talk more about that in a second. So I'm going to very quickly condense about 18 months of work working with Foster and Partners on the design side to get to the stage of design that I will feature. So just to summarize very quickly all of that work, eventually the design was, we arrived at this design where there's an elliptical shape at the base, a different ellipse at the top, and then the massing of the building is an interpolation between those two shapes, and then the facade itself is a spiral panelization around the facade. So because every single floor is unique, since these two ellipses are different, and then the ellipses are biaxially symmetric, but the spiral, of course, is in one direction, and so long story short, what that results in is every single panel is unique and different. And again, to condense 18 months into a very short slide, eventually we landed on cold bending and non-planar quads being the most appropriate design solution for this project. But to give you some statistics on just how large this project is, it's 23,000 individually unique facade panels. The glass alone is 85,000 square meters, 400,000 square meters of total surface area. The maximum out of plane bending on the glass is over 400 millimeters, and in the end, we produced 8.5 million fabricated elements. So one of the challenges was that we had to get from the moment of award to the contractor to the first fabricated element in 6 months. In this case, the facade contractor is Alutech, who we worked very, very closely with. They did the Lusail Stadium. And I think what's important to know is that they are an international organization, and importantly, whereas many facade contractors are kind of they work with a number of subcontractors, Alutech is vertically integrated. So they produce all the glass, they fabricate the aluminum, they produce their own IGUs, and so since they own the entire kind of process, this was an essential ingredient to realizing the project, which will become evident a bit later. And other things, so they have the world's deepest anodizing plant, so some of those shading elements are 2.6 meters wide, so they were able to anodize 2.6 by 6 meter aluminum sheets. PVDF, they have the largest coating plant in the world. They were up to, it says 17, plus the 3 jumbo-sized 20 CNC 5-axis machines in the end, which will become, and a fully automated IGU line. So, working with Alutech, we had to get from the moment that it was awarded to them to the first fabricated element in 6 months. And here's just a sense of the quantity and the geometric variation of the various fabricated elements. And the incredible degree of bending and the variety of panels. You can kind of get a sense of that here. So let's talk about why this is. And I think the most important thing is that the panels are bent in the facility. So there's no on-site bending. They come out of the factory in their final 3D position, which is really important because trying to do this on site means that you have workers 200 meters in the air, winching these panels into place, which requires an incredible amount of force, but most importantly, an incredible amount of time, because the entire time that you're on the building trying to push these panels into place, the crane is holding the glass panel in place, and all of that just drags the program out, and we had only about 2 years to get from the first fabricated element to completion of the facade. So the other thing that's important to know about this is that you can see if I'm pushing up in the right-hand corner, that all of these elements around the frame are twisting. So as you push these things out of plane, they don't just simply translate, they also rotate because they're rotating relative to each other as you put that fourth corner out of position. And as I'll show, the bottom element you can see is twisting, which when you're trying to get a flush floor is also a challenge because the transom doesn't stay flat. You can see here, the mullion in some places was as much as 20 degrees out of plane. You can see kind of the distribution on the left of the degrees of rotation. So, but here's the rub, so to speak. So even if I'm pushing on the far corner, which you don't even see on the screen, the mullion on the left-hand side, which is not the edge being pushed, is still twisting, just because the rotation of the panel is forcing this edge to rotate around its own axis. Now, you can counteract that by changing the angle on the end of the top element. So you can see here the top element, even if I just fix it in place, I can change the angle on the end of that element, and that will help me engineer the degree of twist in that element. So we can specify the angle on that piece, and there's different ways to do that. So on the left-hand side here, you see, if you just built it flat and you push it into position on site, you get this gap, right? The elements twist out of plane relative to each other. So if the one on the left here is already installed and the one on the right comes into it, as you push it in place, they disengage, right? Now, on the other hand, you can come over here and you can say, oh, I'm gonna reverse engineer all of the twists out of every element and everything's just gonna be straight. Well, the problem with that is that the glass is still twisting. So even if the mullion is at the bottom the same angle as at the top, you can see the relationship with the glass gets compromised down here. So we went for something in the middle, which is where you engineer the amount of twist so that the two panels that engage with each other are twisting in parallel with each other. And then that helps to average out as well the relationship to the glass. So here's a prototype showing that. So you can, like I said, you can change the angle over here. The end of this piece is fabricated on a CNC machine, so it's extremely precise. And so what that means is that on the factory floor, there's no measurements. You'll see the mullion twist as it gets screwed in, right? So there's no custom jig or any of that. All the intelligence, all the geometric complexity is built into the cut on the end of that piece, which is done by a machine. So I show this to show that one of the things that was important as we worked with the facade contractor is that this is the glazing tape here. Now you can see it shifted out of plane, which is something I'm going to talk about later. But the important part is that normally this block, which is the glazing tape, sits inside the frame, and this is the silicone. So what became very evident was that what's critical is that the glazing tape can traverse the corner of the panel. So you can see here the glazing tape is coming around the corner. And the problem is, so if you were to just build this thing flat and push it out of plane, like I mentioned, every element twists, which compromises that corner. If you reverse engineer the twist, you get a nice flat transom, but then the mullion and the transom are like offset from each other. So you can do this, we do this very small micro adjustment so that the mullion and the transom meet each other right exactly at the corner, which you can see here. So right here, there's a bit of a deviation here, but right at that moment where the glazing tape traverses the corner, they're bang on. So in order to get that level of precision, you have to develop extremely detailed and accurate three-dimensional models. So I'm going to zoom out a bit to talk about that, because not only do you deliver the model, like once you deliver those fabrication documents, you can't stop, right? Once the factory starts going, there's no stopping that train. You have to just keep rolling with it. So I'm going to zoom out a bit and talk a little bit about how we work on the computational side. So we work in this methodology, which we've kind of called procedural building information modeling. So I think many people are familiar with the term BIM. Oftentimes, BIM is a top-down process. You put your model together and then you apply information to it. We do kind of a bottom-up approach. So what that means is we generate the data from the bottom up. I'll talk a little bit more about that. This was a process that was developed over the course, like I said, of these projects, where we were working oftentimes in tandem with the contractors to deliver fabrication documents, help them, generate all the documents to address all the geometric complexity in these projects. So so you start with the things that you know, right? So you know when the project starts, which is in the fall of 2018, and you know when it's going to end, which is it has to be done by the World Cup. There's no moving that deadline, right? So you know those things. But then there's things that start to emerge, like, with the contract is going to be awarded in spring of 2020, which really means that your design has to be done 6 months before that because you have to tender it. So there's more and more information coming into focus. And then you realize that in order to meet this timeline, fabrication has to start 6 months after that. And then, of course, is the things you can't predict, which is a global pandemic, and then the fact that your global supply chain is going to shut down within a few months of starting your fabrication process. So the point is, you have to be able to develop. We've developed a framework. We work in a way that's flexible and adaptable. And so what we do is we build up the information in these models in an incremental way. So we start with very low resolution elements like a wireframe, and we add metadata to each of these objects. So there's metadata that is inherited in these objects, and as the model gets more detailed and you build more information into the model, you can see the metadata on those different elements increases because it's passed down through the model. So rather than trying to get to a kind of federated model at the end where you have one single model with all the detail, instead what we do is we have a kind of constellation of models. So you start with what you know, and you develop the detail in the model, but you don't throw the other models away. You create this network of models that are in increasing levels of detail with increasing levels of metadata, and then eventually you develop this kind of network of discrete models which are speaking to each other. They have relationships to each other. And I think the important part is that you don't know at the end, you don't know at the beginning what the model needs to look like at the end. You figure it out as you develop the process. And that's why you need this kind of organic network of models. And you can see there's parts here where you get new information. Maybe you get the survey result from the site, and the slab is out of tolerance or it's not where you expect it to be. And so you need to be able to feed that into your network. And there's no way to know that at the beginning, right? So the point is that there's this kind of flexible network of models. And the other thing that's important about that is you can then extract information, right? There's metadata on all these different elements. So here, for example, you can create a map and you can plot the distribution of wind loads on the building. You can extract the panel types. Here we're mapping the kind of curvature of the panels, right? You can export it to Revit if you want. You can create floor plans. You can run a bill of materials from a wireframe because you know how long every element is without having to model it down to the nuts and bolts, right? You have a model that you can access and query at the level of detail that you need. Here we're running a finite element analysis of a portion of the building or the entire building. We can run a glare analysis because we can actually map the reflection of the sun onto every single individual facade panel and every single cladding element from the site to make sure that the specularity of the material is correct. So, okay, we have all that, right? So coming back to this, to the real life project, and how to get to this level of detail in the elements so that we can fabricate them. Again, here just to remind you what these elements are going to look like. You can see here, you can get a sense of the variation and the type of fabrications, the miter cuts, the notches, the holes, the grooves, all of these things that have to be done on the automated CNC line. Every single one is unique. So to generate that, what we do is we start with a wireframe, and the wireframe has this metadata on it. So each wire represents a fabricated element, and it knows exactly the element that it's going to become. And our digital process very closely mirrors the physical process. So you extrude an element, then you make the large cuts out of it, then you locate the holes, and you cut those holes out, and then you do that many, many thousands of times, and you have all of the panels. So it very much mirrors the kind of physical process. Now, some of the fabrications that you see here, you can see here, in just the last kind of 100 millimeters of this element, the number of very specific small notches, holes, grooves, etc. There's a lot of information that has to be captured just in this small end of the piece. So we actually had to develop our kind of a custom algorithm to be able to specifically engineer the angle and miter of each segment. So you can see here, the angle here is changing, but the plane on this one is staying perpendicular. So we can actually, very closely create these highly complex, fabrication elements basically on the fly. Now, the other thing is that holes are quite complicated. There's a lot of information stored. There's a lot of information in order to capture the variety of holes, because if you think about it, if a single fastener putting two pieces together, you have an access hole that the fastener has to go through. You have the part receiving the fastener, which might have a threaded hole, and then you have the hole in the middle, which might be countersunk. So one fastener gives you 3 different hole types. And you can see here, just in the corner of this panel, how much information is required to actually specify the number and type of holes, just in this little kind of square meter of this corner panel. And so what we've done is we're actually assigning metadata not just to the wire and not just to the element, but actually to the individual holes. So this virtual object, which will become a real object, the individual holes on this piece actually know, they have metadata assigned to them that tell them what kind of hole they are, what diameter they are, what fastener they came from. And then because we have that, we are able to then produce 2D fabrication documents of every single part. This is all generated automatically out of our kind of algorithm. And basically we can read in the part. Because the holes have metadata on them, we can extract their position and their information. We can actually create these in a parametric automated fashion, because the object itself has intelligence, essentially. It has metadata on all the individual faces. So all this is done computationally. This is from a different project, but it's relevant. So this particular fabricator, this facade contractor for this project, they wanted to be able to have 3-dimensional fabrication documents. So you can see here, we're generating call-outs and dimensions for every single hole in a kind of 3-dimensional way. And this is important because essentially what happened is, now we don't drive the CNC machines directly from our model. But what we do is we work with the facade contractor, and because we can control the definition of every single hole, it has that metadata on it, we work with them so that their CAM software, which drives the CNC machine, can automatically ingest these parts, and they can work in a way that's familiar to them, and they can quality control their own work. But because we have done so much front-end work to define the geometry of these components, it just gets sucked up. And you can see here, thousands and thousands of fabricated parts get processed through the CAM software extremely quickly. So here's the component with all the holes, all the metadata, and you can see it just immediately transfers into something that can be assembled and manufactured at scale. Okay, so you remember earlier the prototype of those, it took 8 people to kind of screw just one end together. So by the end of the process, you can see here, it takes 3 people, about 2.5 minutes to assemble this panel. And you can see him lifting up the end of it. Sorry, it's a little jittery because I just didn't want to bore you with the real-time video. But all of the geometric complexity, you can see they don't have to measure it. They don't have to push it out of plane. Because every single component is fabricated precisely at the end, such that the panel is forced into its final shape, 3 people can assemble a panel in about 2.5 minutes. All right, so we've got a complex miter at the end to ensure the 3D shape. We've got a micro relaxation of the mullion and the transom to get the glazing tape to traverse the corner, right? And we didn't talk much about this, but one additional benefit of this being in 3 dimensions is that there's no permanent stress in the structural bond, because you're not pushing the frame out of plane after the bonding. You put the glass on, and then you bond it. So now you got to put a piece of glass on this frame. So let's talk about that. Here you can see a very highly twisted frame and a cold bent piece of glass, which is already twisted, conforming closely to the frame. You can see here, this gives you a sense of the amount of twist that we're talking about in these panels. All right. So here you can see a plot of the depth of bending. So some of these are even 500 millimeters out of plane. So some of the panels are built flat. The IGUs are built flat and then pushed onto the frame. But there's about 25%, which the degree of cold bending is so high you can't do that. And so they are warm bent laminated. They're laminated in their final position. I'll show more about that. What's tricky is, normally the way you do this is you have your wireframe definition of the panel. You know where the edges need to be. You would use your three-dimensional software to create the surface, and then you just unroll that panel. You just type in unroll, and you get a nice little flat shape, and you produce a fabrication drawing. The problem is that the surface that most CAD programs generate is not the real surface. So for example, in theory, if you have 4 straight edges, you get this nice hyperbolic paraboloid, which you can see here with straight ruled lines. In reality, you get this kind of buckling shape. You get this slight dimple in the middle, which comes from the stiffness of the material. So we can see that here. So down here, you see a prototype, and you can see the kind of stiffening and flattening of the reflections here in the middle, and the finite element simulation that matches that. So you don't actually get this kind of like beautiful, perfect hyperbolic paraboloid. That's not what happens in reality. So we can actually see here, these are a number of simulations. This is the deviation from the idealized surface. So these kind of bubbles that you see is how the surface is diverging from what you would normally get out of your three-dimensional software. Here it is normalized, so you can kind of get a sense. Like, in other words, here, the brightest white is the peak across all of them. Here it's panel by panel, so you can just get a sense of the type of curvature that's happening. So, we verified this with some prototypes. You can see here, this is bent about 350 millimeters out of plane. Again, this is it's bent, put in the autoclave, and then it comes out of the autoclave. You release the jig, and it stays out of plane because this is using SGP interlayer. So the stiffness of the interlayer helps keep its shape. Then we 3D scan that, and we compare this to our finite element simulations. And so you can see the general morphology of like you get a kind of a ripple here, a stiff flat area here, and then another kind of bulge matches the general contours that we were seeing in our simulations. So another way of just kind of thinking about this, visualizing this in your mind, is that normally you start with a straight line, right, when it's flat, but of course when you twist it, you develop curvature in the middle. Now, if you measure the ends of a curve in a straight line, it's shorter than the length of it when it was flat, right? Kind of makes sense. So the edges are essentially pulling in. And you can see that here in this simulation. So this corner is pulling out a plane, which means its lateral movement is a little bit ambiguous. But you can see on this edge where it's flat, you can see in the simulation it's pulling in by as much as 4 millimeters. And we saw that in the mock-up as well, in the prototype. Measuring from a straight line, you get about 3.6 millimeters. And what we saw in the project ultimately was 6.5 millimeters was the worst case scenario across all the panels on the project. Now, in order to address this issue, I see, okay. In order to address this issue, we have 4 straight edges. Some are curved on the top, some are curved on the bottom, and then we have some that are curved on both edges. So we characterize the curvature across these 4 different types of panels. We can then parameterize that, so we can map the curvature of those edges to the curvature of the panel in the middle. So we take these sample points, and they help us measure or characterize the deviation from the idealized surface to the real surface of the glass. And because we have this mapping function, we can apply a machine learning algorithm to create the relationships from the inputs to the outputs. And so what we do there is we generate a database of 3,500 simulations, which looks like this. And then we basically create a sample space where we interpolate between those inputs and the outputs. This is a bit abstract, but I think the point is you have these sample points that give you a kind of contour. And so if you don't have a sample, if your panel that you're actually going to generate is here, it can interpolate and predict what those values will be and how that characterizes the surface. I'm going to go with a quick list through this. Yeah, so we were able to reduce the deviation because we were able to predict the 3-dimensional surface of that glass. When you unroll it flat, we're able to reduce the deviation from 6.5 millimeters down to 0.5. So you got this very highly defined fabrication model. The panel is twisted out of plane. Now you've got your curved glass. You put that on your panel. We generate these assembly drawings parametrically. Every single element knows what panel it belongs to, so you can do this on the dynamically. And again, the point of all of this was you have panels, and then panels, and panels, panels. We generated 1.5 million individual fabrication documents over the course of about 2 years, which you can see here. And since I'm behind, I'm going to skip ahead. The point of all this is that, again, if you remember, the speed of assembly, the speed of installation. So you'll see here, this panel will go on the building, and the crane will be occupied for all of about 2 minutes, even though this panel is highly twisted, highly three-dimensional. gets dropped on there, and then the crane can drop away. There's no winching. There's no pulling it into place. And you can see here the speed of installation. At its peak, they installed 220 panels in a single day. And that's, cold bent, highly curved, twisted panels. And I'll just let this get to the end there. That's around the 200 per day. You can see it just jumping floor by floor by floor. And then you end up with something like this. That's it, yeah.